So lastly, we're going to attempt to look at an application question where we're going to use a quadratic equation to solve a particular problem. So in this case, uh, we're looking at the curve of a suspension bridge, the Golden Gate Bridge that's in San Francisco. And it can be modeled by the quadratic equations given to us right here. So it tells us that h is equal to a big decimal number times x squared plus bx plus c, where h is the cable's height above the water and x is the horizontal distance from one tower, okay, both in meters. It tells us the center of the cable is 460 meters from the tower and 225 meters from the water. So the vertex of this particular parabola, if we look at the gate, at the bridge itself, the vertex appears to be about in this location. Okay, and we know that this particular parabola, it says that the center of the cable is 640 meters from the tower. Okay, so that means that the distance, and again, this would be, the water is kind of the x-axis. Okay, so that's our x-axis, and this is our y-axis here. So 640 meters, about here. That's about 640 meters away if you're just on the water. And then it tells us that it's 227 meters above the water. So from the water line up to there is about 227 meters. Okay, and so this actually means that the vertex of this particular parabola is at 640 and 227. Okay, so what we need to do is we have to write a quadratic relation that models the curve of the cable first in vertex form. Okay? And what's important is that what's given to us right over here in the question is that this happens to be in standard form. Okay, it's not complete, but it's written in standard form. So we need to actually convert this into, like, based on the information that we have, we need to write this in vertex form. Okay, so we actually know what our a value is. So it tells us, because in standard form is equal to y is a squared, or sorry, y is equal to a times x squared plus bx plus c. So we actually know our a value. Okay, our a value is right here. It's that decimal number. So 0.000549. That's our a value. Okay. Now we got to figure out, well, what's the h and the k value? Okay, so we got to figure out h and our k values. Well, we know that now that we have the vertex of this particular parabola, we know that 640, that's the h value. Okay, because that represents the horizontal shift of the vertex of this parabola, and k represents the vertical shift. And so this is our k value, or 227 meters. Okay, so if we substitute that into our vertex form of the quadratic equation, again, vertex form is y is equal to a times x minus h squared plus k. Okay, if we substitute in our a, h, and k values, we end up with an equation that looks like y is equal to 0.000549 times x minus 640 all squared plus 227. Okay, so what we have here is now the equation in vertex form. So the next thing that we need to do is we need to convert our quadratic relationship from vertex form into standard form. And so we've been working on that over the course of today. And the only difference here is that the numbers happen to be larger than some of the other numbers that we've worked with. So let's take a look at how we actually convert this into standard form. So I'm going to write from again, vertex form. And I'm just going to write that equation out again. So 0.000549 times x minus 640 all squared plus 227. Okay. So again, we have a binomial, and we can use that binomial. The binomial, again, is right there. And so we're going to expand that thing out. So I'm going to write this as y is equal to 0.000594. And then x minus 640 times x minus 640 plus 227. Okay, so now I'm going to use my FOIL pattern, and I'm going to multiply my firsts, my insides, my outsides, and my lasts. So I'm going to multiply, again, my firsts, and then my outsides, then my insides, and my lasts. So that's going to end up with y is equal to 0.000549 times x squared minus 640x minus 640x, and negative 640 times negative 640 is going to equal 640. It's going to equal a rather large number. It's going to equal positive 409,600. And then we haven't dealt with this plus 227 at the end quite yet. Okay, so I'm going to simplify this by collecting my like terms that are in there, the negative 640s. So 0.0005, let's try that again, 0.00549 x squared minus 1280x plus 409,600 with 227 at the end. Okay. So now what I need to do is actually multiply out my a variable by everything that's inside the bracket. So this number times x squared times negative 1280 and times positive 409,600. So I'm going to go through and do that, and that's going to result in y is equal to 0.000549 x squared times, so when I multiply those two pieces together, I end up with, so when I multiply 0.000549 times negative 1280x, that leaves me with negative 0.70272x. And then if I multiply 0.000549 times 409,600, that leaves me with positive 224.8704, and then finally at the end, that 227. So I'm going to clean that up one last time. That gives me y is equal to 0.000549x squared minus 0.70272x plus 451.89. I'm just going to round it up for simplicity's sake. Okay. So the second part, or the last part of this question says, at what height does the cable actually attach to the tower? And one key thing that we need to know about this is that in the equation for standard form, the C value is always the y-intercept. In other words, the C value is where it crosses the x-axis. So in our original diagram, we're actually looking for where does this tower intersect with the x-axis. Okay, and so we're trying to figure out where that blue line and the x-axis represented by that middle tower in the ocean there, where those two lines actually intersect from the vertex. And so we actually have that answer given to us right in the equation because the C value is right there. And so therefore, the height of the cable when it attaches to the tower is equal to the C value. And so the C value is 451 meters and 87 centimeters. Okay, so that's just an application question where you can use uh, quadratic relationships in the real world.